Hello, everyone. Good morning. My name is Esaú Villatoro-Tello. I'm from Universidad Autónoma Metropolitana in Mexico City, and I'm going to briefly describe the participation from EDAP and UAM at the Germ Eval2020, classification and regression of the cognitive and motivational style from text. Our team, as you can see here, is formed by Shantipriya, Parida, Petr, Motlicek, and Qingran Zhan from EDAP Research Institute in Switzerland. And also you can see Sajit, Kumar, who is at the moment in the Indian Institute of Technology in Kharagpur, India. Okay, so I will try to be quite brief on this. The organization of the talk will be a brief introduction, some details about the dataset, then the details of the methodology that we apply for these experiments. Well, I will describe the results we obtained, some analysis that we did at the moment, until now, and brief small conclusions. Okay, so, well, as you may know, the idea of how do we use the language reveals a lot of information about ourselves. So this is an idea that has been in the research community for a long time now. Particularly in the natural language processing field, this is known as auto-profiling. What is the idea of auto-profiling? The goal is to model some general sociolinguistic features that might be useful for identify a group of authors. This is the main hypothesis establishes that this type of features might be indicative of how the authors use the language given their gender, their age, some personality traits, some political orientation, etc. So what we did basically is that given the nature of the OMT task, we assume that the task of detecting motives and its corresponding levels could be an additional dimension of the auto-profiling problem. This is thus the main goal of our participation was to evaluate the impact of recent deep learning architectures, in this case transformer-based, and we compare its performance against more traditional machine learning methods. As you may know now, the best configuration that we report during the test phase is 69F macro, which is a 7.4 relative improvement in comparison to the baseline system that was proposed by the task organizers. Okay, regarding the dataset, well, you all know the details of the dataset. This is a language, German language dataset. The textual descriptions are very short, which is something you can see here. The number of tokens in average is 20 tokens for each textual description. The vocabulary size is also very small. In average, 18 words are used in every textual description, which means that in general the users use very few words and distinct words for writing these descriptions they were asked for during the OMT test. And this behavior is more or less the same in the different partitions. As you can see in the development and the test partitions, we can observe more or less the same numbers. Okay, well, some important detail about the training dataset is that for doing the experiments, we remove 13 instances. We did this because for these instances, we did not have the motive level values for these instances. Okay, so regarding the methodology, before explaining some of the details of what we did, I would like to say that we face a problem as two different classification problems. We train classifier for predicting motifs, and in a second stage, we train a classifier for predicting levels. This is, instead of a 30 class problem, we divide it into 5 and 6 classification problems. For each of these problems, we follow the exact same methodology that I'm about to describe. So as a main approach, we employ a simple transformers architecture to train a classifier on the OMT classification tasks. This means that for this, at the end, what we do is to add an untrained layer of neurons on the end and retrain the model with the OMT task classification task at the output. For these experiments, we set the max length parameter set to 19. This is because we observed that the maximum length on some of the instances is about, I think, 19 actually. The retraining was up to 2 epochs maximum. For doing these experiments, we tried 3 different configurations. Particularly, we tried with BERT encodings, XLM, and distal BERT. Okay, so as the second approach, this is a more traditional machine learning approach. We try a fully connected neural network. Some parameters of this network, as you can see here, the total number of layers is 3. The number of hidden layers is only 1. The number of nodes in the hidden layer is 16, and the activation function is a ReLU function. So for defining the input parameters of the neural network, we have 2 different configurations. The first one is using the last hidden layers, the encodings generated by the last hidden layer of the pre-trained BERT method. And in the second approach, we try with the concatenation of the last 4 hidden layers. So these are the features that are fed to the fully connected network. And in order to obtain these encodings, as I mentioned, we use the pre-trained encodings that is possible to obtain from BERT. And in a second configuration, we use the encodings that are obtained after the fine-tuning of BERT. This is from the experiments that we did from the simple transformers. At the end, we have a retrain method that can be seen as a fine-tuning of the BERT, especially with BERT, and we keep with those encodings for generating this representation. Okay, so about the results. Well, as you know, the baseline method was a simple support vector machine with TF IDF representation. This baseline obtains a 63% F macro and a 64 in the test partition. So for the fully connected network, when we generate the features using the pre-trained models, you can see that none of these results is able to improve the baseline. And the same thing happens in the test partition. But on the contrary, when we use the encodings that are generated with the BERT after fine-tuning, well, results are better. Actually, now it's possible to improve the baseline. And this is also for the case when we use the last hidden layer in the test partition. Here, this number, the 0.23 of macro, actually it was quite a surprise for us because, well, I must confess that even now we are still not sure what happened here. for sure we need to double check what was the error on this configuration. Okay, regarding the simple transformer experiments, well, as expected, these methods are quite good in comparison to the fully connected network. Especially the best configuration was when we used the BERT encoding, the BERT architecture. But difference among methods is quite marginal. So if we wanted to decide which one represents the best trade-off between computational cost and performance, probably distilled will be a good choice. Okay, we tried to do some more particular analysis of the obtained results, and for that what we have here is a confusion matrix for the motives prediction problem. And as you can see, the simple transformer is able to improve the results from the baseline in every motive except for the zero motive. In this case, we are losing accuracy in this part. But other than that, we are able to obtain important improvement in every motive. Same thing happens for the levels. As you can see, we are able to improve the numbers in every single level that exists in this classification problem. But well, in this case, we are able to improve the zero level, but the difference of the number of instances actually is quite low in comparison to the rest. So we think that maybe the zero motive might be a bit difficult to accurately to detect. As an additional type of analysis, what we do is we try to evaluate or see where the attention is being focused for each of the models that we consider. In this case, we are comparing the pre-trained BERT and the fine-tuned BERT, how the attention mechanism is being modified after the fine-tuning. For this, we randomly select 4 instances. This is the motive level combination for these instances. And as you can see, well, the fine-tune is actually is quite notorious, the modification of the attention. As you can see, we are losing some attention of some punctuation marks. Also, the same thing happens here. This, for example, you can see this is not there anymore. These 2 points are not important for this fine-tune. But the important thing perhaps could be to focus on this type of words. Ist, the, there are getting more attention. Actually, as if you compare these images, you can notice that the intensity of the color is higher here. Also in the negation parts, we observe that for some examples, negation words are getting more attention in comparison with the pre-trained encodings. So this is interesting. Perhaps we think that an interesting analysis could be done in this direction, and how the attention is being modified, and what is the difference between motives and levels, and perhaps try to make a correlation analysis with this and what the expert psychologist is observing in this textual description could be interesting to do. Okay, conclusions. Well, as expected, the simple transformers exhibit the best empirical results. However, there is plenty of room for improvement. We consider that detecting these motifs and levels from these very short descriptions actually is quite a challenging task. These very recent technologies are not able to obtain a significant, very high performance. So we think something else can be done here. regarding the analysis of the results, well, what we observe is that the attention mechanism is paying more attention to some stylistic features. Some functional words are getting more attention instead of content words. And finally, well, we have our doubts about the meaning of the motive 0 and level 0, which are the instances that are more difficult to accurately classify. Perhaps there are some noise in these elements. It will be good to know what is the exact meaning of this in order to make further decisions. Okay, well, thank you very much for your attention. If you have any doubt, I will be happy to answer. Or if you want to know more details, also you can send us an email or contact us by Twitter. Thank you.